Hello dear colleagues, I am Taya Balberg. Today I will present to you our recent study about miniature and light fuel cell energy pack based on hydrolysis with atmospheric humidity. This study took place in the Fluid Dynamics Lab in Ariel University, Israel, by a research team supervised by Professor Schechter and Professor Idit Avrahami. With the development of technology, the need for mobile energy sources that are light, portable, and have high energy density has increased. Many of those devices and sensors require nearly continuous operation for long periods, days rather than hours. Batteries are currently the power source of choice. However, weight and size constrictions usually prevent current batteries from powering long-range or long-duration missions. Batteries can provide relatively high power for short periods, but the total energy they can supply is limited due to their size and chemistry. A better alternative might be energy produced from fuel cells that are driven by hydrogen. This alternative has much higher value of energy capacity, energy density, and specific energy. A common fuel cell is a device that produces energy from reaction of hydrogen and oxygen to produce water vapor. For example, this proton exchange membrane fuel cell is equipped with an Nafion selective membrane that prevents the hydrogen from reaching directly with the oxygen and allows harvesting the stream of electrons to produce electrical power. The main limitation is the hydrogen carrier. Hydrogen is a very explosive chemical. High energy storage of hydrogen requires extreme conditions like temperature and pressure. Compared to batteries that has relatively low volumetric and gravimetric density, hydrogen can provide energy at higher densities when carried in tanks. The use of metal hydrates as a source of hydrogen suggests much higher densities. In this study, we suggest to produce hydrogen by a chemical reaction between metal hydrates and water vapor extracted from the environment's humidity. The suggested device is a novel light energy pack that uses lithium aluminum hydrate powder inside a bag. This combined energy pack includes a hydrogen generator and a fuel cell that uses the generated hydrogen and atmospheric oxygen to produce electric power. The device is equipped with a selective membrane. This membrane allows to keep the produced hydrogen from the reaction inside the case while allowing the water vapor to go through and penetrate the system. The produced hydrogen is then reacting with the outside oxygen over a membrane electrode assembly, MEA. The anode and cathode of the MEA are assembled on both sides of the membrane, covered with a catalyst and a flat plate electrode. The reaction over the MEA results is electric power and water vapor on the outside. The goal of this study is to characterize the performance and efficiency of the suggested device. We especially examined the effect of membrane thickness, membrane area, relative humidity, and heat regime in the bag on hydrogen production rate and leakage. 3 prototypes were used in this study: a reusable system with a syringe, a system with the disposable bags, and a combined system with the bag and the MEA. The syringe prototype setup was combined to examine the impact of the membrane thickness and area, and the effect of the humidity on the hydrogen production rate. To measure the parameters under fixed and controlled conditions, the experiments done in a fixed temperature incubator and humidity was regulated by a humidifier. Hydrogen production was measured using a cylinder and recorded using a GoPro camera. The reaction temperature was measured using a thermal camera. In all the experiments, membrane diameter of 20 mm was used and 0.25 grams of lithium aluminum hydrate was placed in the serine. Here is an animation describing the system with the pack, the cylinder, the thermal camera, the data logger and the GoPro camera. The results show that for thicker membrane, the reaction was faster than thinner membrane and more hydrogen was collected. We assume those results imply of two mechanisms. The first is related to hydrogen permeability through the membrane. Thinner membrane allow more hydrogen to leak to the environment. The second mechanism may be related to heat transfer. Since the reaction is exothermic, the temperature inside the serine increases with the reaction rate. Thinner membrane allow better heat transfer with the environment and the temperature inside the serine should be lower. The assumption of membrane permeability was examined by measuring the hydrogen pressure drop over time. Higher pressure gradients were observed in the thinner membranes, in all the diameters. This shows thinner membranes allow more hydrogen to penetrate to the environment and less hydrogen is collected from the reaction. To estimate the effect of the heat convection through the membrane, free convection from horizontal plates was assumed. The calculated Rayleigh number for the case is large, showing the system is driven by a natural convection and the temperature distribution inside the bag is relatively uniform. Thus, we can assume that the measured temperature from the experiments represent well the reaction temperature of the powder. Most of the heat is removed through the hydrogen gas, but the heat transfer through the membrane is a critical parameter in the heat regime. Thicker membrane allows higher temperature inside the serine and faster reaction rate. The bag prototype was built using disposable bags to which we glue the membrane. The water vapor went through the membrane, reacted with the powder, and the produced hydrogen was released through a tube. The measuring system included the bag with the powder in an incubator. The hydrogen flow to the cylinder was recorded. Here is an example movie of the recorded experiment showing two bags in the incubator. You can see the bag inflated with hydrogen and the cylinders filled with hydrogen gas over time. The monitor shows the reaction temperature measured by the thermal camera. The results with the bag show consistent increase in volume with slightly higher flow rate in the thicker membrane. Humidity has a small effect on the flow rate as well. The average reaction temperature is higher for the thicker membrane and higher reaction rate. The next stage was to combine an MEA with the bag to produce electricity. The system included a membrane to keep the hydrogen inside, MEA, electrodes on each side of the membrane to produce electricity from the reaction with oxygen. A rigid case with a blocking sheet is added to prevent the bag from overinflation. Here you can see an example of the bag with the MEA and a LED. With our characteristics, the energy pack provides a current of 100 mA for a resistor of 8 ohms and a 3 volt DC. The presented results demonstrate the basic possibility of this approach. These results show that the hydrogen production from lithium aluminum hydride can be regulated by a membrane type. For a better performance of a thicker membrane should be used. This type of membrane is also easier to employ due to its higher strength. Our work includes design and optimization of the mechanical control systems for long working periods in different conditions. Experiments carried out to prove system efficiency in order to allow various applications. Our results show that hydrogen production is sensitive to naphthalene type, relative humidity, temperature, and pressure. Experimental results under controlled humidity demonstrate an effective utilization almost 100% of the theoretical hydrogen using this system over 72 hours. I would like to thank to my wonderful team and the Ariel University for the grant. Thank you so much for your attention.